So the other lecture that I posted up on YouTube today has some, you can see this, some description of this tree of RL algorithms, and specifically explaining how we got to kind of where we are, and going through kind of the first big algorithm that used reinforcement learning and deep learning, which is this. As I said in that video, kind of things we talked about in the course mostly focus in on this area of types of algorithms, where we're doing model-free and doing things based on Q-learning, or as I said in that one, sort of value function-based, which is more general than Q-learning. Or doing direct policy search, right? And so you can do these with your value function being tabular, or being some kind of function approximation, or you can do the policy as I should undo that because it's unreadable. And you can do the policy as some kind of function on the V or Q, right? Like max or something like that. Or you can represent explicitly as a value function approximation, where you actually represent some kind of policy pi SA with parameters theta, and we had some little lectures on how that can be represented. And so once you do that, you can represent all the stuff in reinforcement learning, the same kind of Bellman equations and things, as a function of this policy. And there was a lecture and notes on that. We're going to review that a little bit today and talk about how to do it with neural networks. Because it doesn't change much, actually. Just change essentially what the parameters are. So there's this explosion of new algorithms, and as we talked about in the other one, this was just 2015, and all of these have come after that. But this DQN, the first one, was using the value function approach, where the neural network represents the value function, and then you do essentially Q-learning with that. So the other major branch of deep RL algorithms is to use this policy optimization approach and use neural networks in some way to represent the policy and then optimize that. And then there's lots of newer algorithms also coming out, and it continues actually ongoing. This tree is from 2018, so things have happened even since then, where they try to do both and use the representation of the policy and the value function. So what I'm going to talk about now is basically review this and talk about this A2C, A3C, which is the other algorithm that we're asking you to do on the assignment. So some of the slides kind of reviewing policy gradients. Again, if you went through that, or it's always good to go through things again to get it solid in your mind. Let me get this open in another view so I can see what's coming. It'll look better that way. Okay. So, like I was saying kind of there already, there's two different major ways to represent your reinforcement learning, learning of control. We can have an action value method where we're learning that value function, or we can learn the gradient, the parameters of this policy directly. So somehow first have to represent the policy in a functional form that has parameters, and then we're going to compute gradients, like calculus gradients, like weighing to optimize, so that we can incrementally change these parameters of this policy in order to improve it. So we kind of search for the right solution. So one way to see these all together is to talk about the kind of overlap of that. So your value function, Q or VSA, QSA or V, sorry. And then you have your policy, which I guess I wrote different ways, but it's got some states, and it predicts an action, and has some policies that tells you how to get there. And in this sweet spot between them, where you're using a bit of both, is these methods called Actor-critic. That's kind of what we're going to focus on, because that's the way people implemented them in the first deep RL methods to use policy gradients. So an advantage these have is I'm sure that I'm disagreeing with our best convergence property slide. I guess this came from a tutorial online, so it must be true. Does it always have better convergence properties? It has better theory of convergence, but right. So they're actually claiming that too. You never know if it's optimal, right? So you're converging to something, but you don't know if it's going to be just some local optima or something that's actually close to the best policy you could have. But they are very effective for high dimensional spaces, and it makes continuous actions spaces more easy. So if your actions are continuous, or the space is very large, you can just, whatever way you can represent this function, it's easier to represent it, rather than have to enumerate all states and actions, put them in some big space, because the thing you're optimizing here is the thing that you actually want as your output, right? When we do the value function approach, we're optimizing learning, this function represents kind of our sense of which states and actions are good. What we really want is the policy. So we use argmax or greedy or something to extract the policy from the value function. But why not optimize the policy directly? Well, some of the reasons are it's hard to make sure it converges to the global optima, and you could end up being searching around in circles, but it's much more direct. So, like I said, these are some review slides from, these were in the policy gradient, I think, lecture already, but a simple version of this, of a policy, would be this gradient bandit approach, where you define the policy as just something that takes an action regardless of the state. So it's kind of very simple and kind of strange from our point of view now, because there's no state listed. I thought we had one listed, which was, where there's a state given. So, I mean, just the main point here is that you could represent a policy for acting, right, as a probability distribution, where you're just going to have this exponential kind of logistic function, right, which is kind of anything in general. You're going to have like this. This will give you a nice probability distribution. And then the question is, what is your function going to be? And so we can have a function f that just describes whether you like some actions more than others, right? And this could be something very general. It basically gives you a preference for certain actions. And so if we have actual states, then the preference could be like, we found that action, taking that action in that state, gave us a higher reward, or we often had a higher reward in that state, or we had a higher return because we kind of back it up. So it's a very general approach to building a policy, where as long as that function makes sense and can turn basically some function of states and actions into a preference for saying, I'd prefer to take this action over that one, then you can represent a policy this way, and it's very general. Now these weights could be the weights of logistic regression function or a decision tree or a neural network, right? As long as they're something that give you an output number that you're going to use to compute the policy, you'll get a probability distribution from it. And so the simple form of that, the gradient then, like we said, when you're doing policy gradient, we can define our policy. The nice thing about this function, so why this gets used, is that we know the derivative of it, right? An important part is you can define your policy any way you want, but you want something that's differentiable, right? So as long as it's differentiable, then you can derive the formula for updating the weights, right? And so now we're doing a gradient over theta for the policy. And I must have on a later slide, I took out some slides, sometimes the important one is missing. Okay, something like that, yeah. If this becomes, if we're calling this as a function, later on we're going to call it this, so I'll just call it this now. We've got some function j of our policy and our parameters. When we say that's the gradient of it, in order to update this, we literally just are going to be updating our the parameters of our policy, right? That doesn't work. And with some weighting, and then we have this gradient, just to have it kind of all reviewed there directly. Right, so the simple idea is that, you know, these weights describe your policy, and you're going to be updating them incrementally based on some derivative of your function. And if you think about what that means, right, we're basically building a probability distribution based on some preferences, and we're really saying, for this action, here's the probability of taking that action. For action 1, it's probability 80%. For action 2, it's 20%. So you pick the one that's best. The gradient says, if I changed, you know, parameter 17 a little bit up, would the probability of this action go up or down? If I change the probability of 248 up, would the probability of this action go up or down? And so it's the gradient, right, is this relationship between a very small infinitesimal change in the parameter and whether it would make this action more likely or not, right? And then you can see how, if you can basically say, oh, that was a good action, whatever the agent did was really good, I want to take whatever that policy is and make it more likely to do that again in the future. Or if I got a bad reward, I want to make it less likely to do that again in the future. And so you move the weights in the direction that would make that action more likely if it was a good action. And when we're talking about a neural network, these weights, there's going to be thousands and thousands of them, but they're still just weights that define what you should do, whether you should follow the policy that currently exists or improve it. So I don't know if we need this. It's more about performance of the various very old, like, classic algorithms to reinforce kind of this first algorithm that did policy gradients, and showing how different aspects of that formula basically are important. But getting us closer to what we need, so we've got our objective here is what we're having. We've got our update to our parameters, which I was just describing. And the closer version to what we're going to be using is like this, right? So you're going to have this gradient that you want to compute so that you can figure out how to change your parameters. And you've got some function that has a sum distribution over all the states it could be in, all the actions it could take, and then using our usual value functions and policies from a Bellman equation, but in this relationship where we just multiply the value of that state by the policy. And so this, in the original lecture of this, we derived how you get this a bit. What's important is that you don't need to know the dynamics, right? The great thing about policy gradient is note that you don't need, I don't even know what we're calling it in this domain, but you don't need PS prime SA, right? The dynamics, because the policy is enough. So, but this part is important for us to see how it works in the deep learning part, because there's something that gets added for stability, which is called a baseline, right? So what's a baseline? Baseline helps it kind of not veer off course, basically to add stability in the search, right? So remember, we're searching in this very high dimensional space of these parameters of an entire policy, which is some distribution and maybe a neural network, and we're making small little changes up and down to different weights. Great. The next question was about baseline. So it basically gives us, so because if you in the default version of the math, when you derive it out, you get this thing where you say, well, the gradient of the policy is literally this distribution over all the states, the value of that particular state action you're looking at, and this gradient based on your policy. And you can follow that, but it's very finicky. Like you'll get very like ups and downs and everything, and you'll be chasing all of these, and you end up getting stuck. What the baseline says is pick something stable, something that isn't changing that quickly. And then instead of chasing the value of your particular action, chase the difference between your action and that, right? And so you can think about this as giving you something like, did it go up or did it go down? You know, like what's the main thing that happened? That this value was positive or negative compared to your baseline. And the baseline technically can be anything, but in practice, picking a good baseline makes it much more effective. And so what did we say that here yet? Current value estimate, a good baseline, is to basically just use phi, right? And so here you'd have Q minus phi, right? And G here is supposed to be the return, right? Yeah, this is what we're basically getting into, because the way it works then, well, if you can see how maybe that would make things more stable, right? So rather than chasing the actual value of taking this action, you say, well, I know that being in this state, regardless of any possible action it could take, has a certain value, right? Because B, if B here is going to be replaced by V, I don't know why we would have lowercase v that way, but let's say that B equals, you know, just the way we think of it currently, V, right? But under the current policy, I guess that's what the W is. Then we're saying, is taking this action gonna be better or worse than the average discounted expected value I would expect from this state, right, before I took any action? So this might sound familiar. We talked about the advantage function before. We're gonna get back to that again and redefine it to make sure it gets used. So the baseline helps stabilize that, and then the updating is like, there's the learning rate, which I used before but didn't mention, which tells you how aggressively you want to follow your new experience or not, right? So when you use baseline, things converge much more quickly and stabilize, even with the old classic algorithms. This is from the textbook. Yeah, so this idea of an actor-critic now, we're kind of getting closer to it because now we've got this baseline thing, we're subtracting two parts. So we're starting to see if like a policy gradient isn't just having some parameterized policy and doing gradient descent on it and optimizing it. The metaphor people use is to talk about an actor and a critic. And the idea in our usual scenario of RL, right? We've got the world, there's some state, we take an action, and we get some rewards. The rewards over time help us estimate this value function, and somehow we're using the differential errors or changes from that value function over time to help us choose the policy. So that's one way you could see a lot of algorithms. But now we're going to start calling these things actor and critic. And that terminology is just another way to reframe what we've already been doing, but to be explicit about it. And in the deep learning approach, we're basically going to have like a neural network for each, one for the actor, one for the critic, right? So the actor is the agent that's trying to make take actions, right? So it's the policy, right? The actor is the policy. They have some parameters that tell them which action they should take based on the states. That could be a probability distribution. And then the critic is what basically evaluates what that actor has done and says it's good or not, right? So the reward does that directly, but that's the environment giving you the reward. Now we're going to say we're going to have a model that evaluates the policy, and then we come up with a weighting, like a positive or negative, and a scale that we're going to use to weight the gradient itself, because we're using the gradient of the policy, to figure out how to change the weights, of our policy. But we still also want to weight this by something and say, well, should it be good or not? And so rather than it just being Q, we're going to have this critic, right? And the first basic version we had of that critic was version 1 or version 2, I guess, was the Q minus the B, right? With the value function. But we could have something even more complex. And the idea is then you have these two elements, right? You have the actor who's doing things. You got the critic saying, no, that wasn't very good. Yes, that was good. And then the actor improves, and they're both feeding off each other, right? And the critic learns as well by seeing what the actor's doing. So they're both learning and estimating something. But you could just see it as Q and pi, which we've already had. I guess from that Venn diagram I had at the beginning, it kind of clarifies, right, that we're essentially doing, when you're saying actor-critic, you're doing both, right? We're going to have a value function, but we're also going to represent the policy explicitly and have them inform each other. So just to remind ourselves, with this Venn function, it was done in some places. It's related to this, the TD error that we've had, right? So we have this temporal difference learning, right, where we said that we're taking the value at one time step and then subtracting the value at the previous time step. But from the, I had a better slide somewhere where these are all in step, right? Where we've got, what was it? It's the target, right? It's the target. Yeah, this is the target. And I forget if we called it the value before, but it's the current estimate of how you're going to do, and the target is what you've actually seen, right? Because you get the reward from an actual experience. You have a discount because you're going to say what's going to happen in the next step, and now you use your model to say, well, I expect this to happen next if I take this action, right? In some cases, we had a max here instead. There's different ways to do it. But you've got now, we're going to call this delta, just lowercase delta if you're doing it in LaTeX, which gives us this difference between the target and the value, which tells us how much this action was better or worse than what we expected, right? So the Venn function kind of summarizes that into a more general form, where we're just saying the difference between taking current action with our value function and averaging over all the actions and just using V is this advantage. And this is what we're going to use to define the relationship between the actor and the critic. So an actor-critic method, you basically explicitly represent so this is the one we talked about before using the old original policy gradient. But now in actor-critic, we're going to have one-step return, which is what we just have there in the previous slide, right? It's the reward plus gamma plus the value function for one step. Could be V or Q, but it's the one step return. And then we're going to subtract the actual value function for the current step, so what we expected before we took any actions. And this difference then becomes what we're using, right? We defined it as delta in the previous slides, so we're just going to use delta. And then you have some gradient of the policy, and that's what's being used to figure out what direction every particular weight in your policy should go. But this weighting of learning rate times delta, which is the advantage function, tells you whether it's good or not, right? This is the part, you know, how fast, I guess that's the way to say it. Alpha is telling us how fast to learn. Delta is telling us whether it was good or bad, the action itself, right? And then assuming we know whether it's good or bad, the gradient is giving us kind of up or down for every weight, right? Each parameter, would be more general, say for each parameter of the policy, right? And so they're all independent things that get calculated separately, and obviously we add them onto the current policy, just to be explicit, right? So we're really just incrementally improving it, and that's actor-critic. In the essence, that's the whole thing, right? What else do we have, though? There's more details. You can see how it's done in deep learning. This is an older slide. Yeah, I meant to remove this one. So it was used in lots of different ways, trying to define different functions that way. But in the deep learning kind of literature, and this is the one that is called A3C, which came first in 2016. It basically does exactly what we're saying there, and explicitly represents two sets of parameters for the policy and for the value function. They use the same neural network that they have in DQN, essentially, and then kind of have the two of them feeding each other, and so the formulas come out different. But that's the main way it happens. The other major differences they had from DQN was that they didn't use this experience replay idea. So if you watch the other lecture, experience replay, they had to add more data, or neural networks require a lot of data to train, and they are unstable if you give them a very small number of data points, and you want to resample data points so it can kind of keep stepping in the right direction to learn about an experience over multiple kind of views of it. So the way they did that was to randomly sample all of their history and just keep basically thinking about the past. So almost DQN plays a game and it's learning, but it's also constantly rethinking over things it did in the past and trying to learn from them and improve its policy. But it does that randomly. So it's experience replays to randomly sample previous state action pairs, tuples, and do more training. With this algorithm for Actor-critic, they didn't do that, and instead they had another approach to kind of stabilize it with more data and randomness, which have many different agents, right? And so instead of having lots of your own history, they have many agents all trying to learn a policy and then sharing their policies, right? So you'd have different agents working in different areas of the state action space of the domain, and then they'd share their data policies every once in a while and kind of converge. So that had the same kind of stability, and it was a very powerful method. But quite soon after, when OpenAI was trying to implement it and give it to people, they kind of looked at it and said, well, why do we don't even have to do this in parallel? You know, many agents, but they didn't have to be in parallel. So initially, these agents are all actually simultaneous. simultaneously acting. And then the new version, A2C, basically does them in serial, so they wait for each other to finish, but it has the same effect in terms of how it runs. Here's pseudocode. So this web page here has a nice description of it. They have a good summary of lots of algorithms, so it's a good resource for you guys. I'll just show it here. I had it ready to show. Oh, that is a different browser. So on this website, they have a whole bunch of different policy gradient algorithms and explaining them kind of in enough detail to understand what the formulas and a good description and links to the papers and pseudocode and everything. So it's a really good kind of outlay of the algorithms as they go, and it's quite up to date. They've added, oops, sorry, I will stop scrolling. They've added some quite more recent ones, so it's a good way to kind of just progressively go through this and see what's been happening. We're talking about this. So they have the pseudocode for the original A3C, and you can look at the paper for that on the original paper, but their pseudocode here is maybe a bit more straightforward with the hindsight, the benefit of hindsight. And there really isn't that much more to it in the sense he's initializing these parameters, looping through time until you decide to stop, whatever your threshold is. And then at some point you're picking actions, right? So you sample an action from your policy. Your policy is going to be represented using whatever function you choose, but it can be represented as a DQN network. And then you receive some reward and some state, and you're going to update the times so that you can see time moving forward. And the main kind of update then is that you go over updating rewards based on, I guess, just the way they've indexed it. You're getting 0 if the game has finished, and then your current value of V is your R otherwise. And then RI should be the old value that you copied over, right? R is your current value that you just computed, and RI would be the one that you had when you started. And so then you get this advantage function R, and that's just being used in both the formulas to basically update the weights of the policy and update the weights of the value function. And they just have slightly different forms here. And when your policy is represented as a neural network, then getting the gradient out of it is one of the standard functions you can get because that's used in backpropagation. So getting a gradient is quite doable. And really what you're doing here is just running backpropagation with this weighting of it for the advantage function. And then for A2C, it's the same, except that they change this being synchronous. They basically, each agent updates things individually until you are complete. And then you run the next agent. Let's see which variable here represents all the agents. Yeah, like we said, the only difference in A2C then is that the agents are run separately, and you just add them together after they run. So this helps because you can run it on a CPU. You don't need a fancy GPU or anything, but it works just as well if you do have GPUs. So I was trying to highlight here what kind of different parts of the theory correspond to that code. So that's what I was doing on the web page. So we got our TD error there, and the main difference is how they're getting updated between the two. And then, so on this page in OpenAI, they have a description of the algorithm and the code, because they kind of came up with this version that's not parallelized, and various performance plots showing how they work better than other ones. And this is on a bunch of the Atari games that I talked about in the GQN video, trying to improve beyond that. But then some of the other algorithms, so PPO is the one that does really well in certain domains, especially if it's more continuous actions, because it's a more pure gradient approach. But then on something that isn't as hard, like Space Invaders, they all do fairly well. So it depends what makes the game hard. You can see A2C actually doesn't do very well in certain ones compared to other algorithms. And so actually this tennis is probably fairly similar to our slime ball assignment 2 thing. So maybe people will find that running PPO or some other algorithm could do significantly better than A2C. We'll have to see. So that's talking about this aspect of policy gradients. Hopefully that's useful for people. And I will stop it there. But at the end of these slides, there's a whole bunch of the links that were used in it, which you can find useful. And as always, those links are also up. I posted them into Learn, but they're also on the Ginkgo tree for topics, which has been updated a bit here. I know it's out of sync from the original plan, but with this deep reinforcement topic, some of those links are in there as well. So hopefully that's useful, and we'll talk again later.